We chemists see the world in a different way. This perspective comes from continually connecting what is happening on the macroscopic level that we directly experience every day to what is happening at the atomic level. At the atomic level, the smallest unit of a substance that still retains the properties of that substance is called a particle. In the case of the silver in my ring, the smallest particle that still resembles silver would be a silver atom. That atomic scale is an amazing hidden reality. We can't even see it with a microscope. This hidden reality has been under humanity's nose since the dawn of time, but was only discovered relatively recently. Since then, our grasp of that atomic reality has led to exponential growth in science and technology. We chemists work at the atomic scale all the time. Out of necessity, we've developed a special language that makes it easier for us to think at that scale. It also makes it easier to communicate our ideas to others. Part of that language is the name we give to the particles present at the atomic scale. You've already seen how the periodic table gives names to each of the different types of atoms. Additionally, atoms can bond together to make larger particles called molecules. The language of chemistry includes the names we give to these molecules. For example, you've probably heard H2O as another way to refer to water, like the glass of water I have right here. H2O is a molecular formula. It means that water consists of molecules, each of which is made up of 2 hydrogen atoms, that's the H2 part, and 1 oxygen atom, that's the O part. We can think of these molecules as particles of water because an H2O molecule is the smallest amount, or part, that has the key physical and chemical properties that make water what it is. So what about when we boil water? Like you can see happening in this kettle. Well, the water molecules spread out from one another to make water vapor, also known as steam, which you might be able to see coming out of the spout here. But the molecules themselves remain intact as molecules of H2O. The chemical bonds that bind the hydrogen and oxygen atoms together are still firmly in place, so the molecules themselves remain the same. They're just spread out from each other a bit in vapor form. Similarly, when water freezes, like with these ice cubes, the molecules of water remain intact. The bonds between the hydrogen and oxygen atoms remain the same. However, at the atomic scale, we would observe that the molecules of frozen water are packed together more tightly than the water molecules seen in the steam. Like boiling, freezing is just a physical change. We call liquid, ice, and steam different states of water. But we've also seen water molecules represented in 3 different ways. First, at the macroscopic level, what we observe in the real world. Second is at the atomic level. These are the particles that we can't see directly with our eyes, and so we show with illustrations or graphical forms. Then our third view of matter comes in the form of symbolic language, either as chemical formulas like H2O, mathematical equations, or as simplified drawings. These 3 views of matter, called a Johnstone triangle, named after chemistry professor Alex Johnstone, represent a model we'll consistently utilize throughout this course. Okay, enough of water. Let's put this away. What about a different molecule, like sugar? The sugar you might put in your coffee, sometimes referred to as table sugar, is composed of the molecule sucrose. We write it as C12H22O11. That's because each sucrose molecule has 12 carbon, 22 hydrogen, and 11 oxygen atoms. This makes the sucrose molecule significantly larger than a molecule of water. The sucrose molecules in table sugar are packed together into a kind of 3D grid known as a lattice. However, when we dissolve sugar in water, like so, The individual molecules remain intact, but become dispersed throughout the water as the lattice breaks up. This results in a mixture of intact water and individual sucrose molecules existing together in solution. So it makes sense to say that in a particulate view of sugar, the particles are sucrose molecules. How do we know that the sugar molecules are intact? Well, we can separate the sugar from the water either by boiling the water out and leaving the sugar behind, or, more deliciously, we can put a stick in the cup, and over time, the sugar will cling to the stick, separating from the water and making candy. You should try it at home. So now let's take a look at the three ways we've seen sugar depicted. There's the macroscopic level in the real world, the atomic level illustration, and finally the symbolic language of the chemical formula, which is C12H22O11 for sucrose. Knowing what we know about sugar, what do you think would happen when salt is dissolved in water? Interestingly, the results are a bit different. Join us in the next video where we'll explain why.